Hello everyone who is attending these webinars for the Earth Observation Cloud Credits program of GEO and AWS. My name is Jimena Juarez and I work in the National Institute of Statistics and Geography of Mexico. I am most honored to present to you the project Earth Observation for Sustainable Development, and I am in the company of my friends Michael, Everardo, Julian, Mariana, Ixel, Eric, and Omar from CONABIO, the National Commission for the Knowledge and Use of Biodiversity in Mexico. Rather than stating the problem, the quote on the screen is here to help us to properly dimension the problem. Ecological degradation and the rapid loss of habitats and species challenge our very existence. Defaunation is one of the most neglected aspects of ecosystem degradation due to the difficulty of its measurement and study. In order to build a truly integral biodiversity indicator, we propose to fuse satellite Earth observations in the form of land use and land cover maps and in situ sensor data, mainly camera traps and sound recorders on over 400 sites in Mexico. However, additional photos, videos, and sounds have been collected in over 3,000 sites from the period of 2014 to 2018. We call this integration the Ecosystem Integrity Index, which we believe should be on equal footing with the GDP. We also envision that stakeholders and policymakers will be able to visually grasp the repercussions of ecosystem degradation processes like deforestation with a special data cube-based tool. This solution is divided into three work packages. A first work package to detect and classify fauna. A second work package to process satellite images in order to produce land cover and land cover change maps. And the third and final work package to produce the tool that will allow the visualization of these changes in the territory. In this slide, we can see some of the results for work package 1. Specifically those that focus in the use of deep learning to detect and classify Mexican bats based on ultrasound data. The graphic shows us the detection rate for different species. The first objective of this part of the project was to develop models for detection, segmentation, and classification of bat calls. A secondary objective was to test different architectural traits for regularization of convolutional layers. We used fully convolutional neural network as a backbone for all models, and all experiments were performed in parallel using Amazon SageMaker platform and single MLP3 2x large instances. And thanks to its fully convolutional properties, our detection model can also yield explicit time-frequency segmentations over spectrograms from which binary masks and bounding boxes can be produced. We found that test results for different versions of channel dropout within classification show that uniform dropout is the best regularization approach for our case. Classification results are still preliminary but very promising, considering that the taxonomic range of over 90 species constitutes the largest classification attempt for bat calls up to the moment to our best knowledge. Additionally, we have been able to observe that confusion matrices built for alternative grouping schemes show that useful ecological information can be obtained even when species-level classification is not possible. With this slide, we jump to the results of Work Package 1 that focus on the use of camera trap videos for the detection and classification of fauna. As most of the video data do not contain animals due to the camera being triggered by wind-induced movement of branches, we start by answering the basic question: is anything of interest contained in the video? And if the answer is yes, we then proceed to find out what it is. All videos were processed frame by frame as images, establishing bounding boxes like the ones you can see on your screen with the megadetector model. Within each box, the detected object is classified as species, genus, or family. The most frequent label amongst all frames was then assigned to the respective video. Additionally, for the ensemble model, coordinates are used as an input to describe potential occurrence of each species to the model. Both models classify 49 species, but the level of classification is defined by the uncertainty. Results below a certain threshold get classified as genus. A lower threshold is used for family, and for results below a third and even lower threshold were not classified at all. Here you can see the results for the species level classification. This next slide shows the results for genus level classification. And in this slide, you can see the results for family level classification. We currently do not consider the occurrence of more than one species and/or individual per video, but this will be our next step. Moving on to the status update of Work Package 2, which regards satellite data processing for land cover and land cover change maps for 5 states. The slide that you are looking at right now shows results for the state of Veracruz as an example. For this task, a crowd mapping platform has been provided to receive rapid feedback from the users on the products. It's also worth mentioning that based on the original MathMax classification scheme of 31 classes, we could discern 4 additional land covers and 15 crop types at satisfactory accuracy levels of 75%. And finally, this next slide addresses the status update for Work Package 3, a public mobile and web-enabled tool for the visualization of changes in the territory over time. So far, the whole Landsat archive for the national territory has been fed to INEGI's institutional Open Data Cube instance, which implies around 90 terabytes of data. Regarding the content to be displayed in this app, with this massive data array, 30 annual summary mosaics were generated. These products are called GEO-medians, and their total volume is around 1 terabyte. Additionally, an internal INEGI review process was launched to have the data and tool compliant with regulation. Today, the public visualizer, together with the corresponding documentation and tutorials, can already be found in the link shown in the screen. In this example animation, we are looking at the change over time in cities like Aguascalientes or Cancun from the year 2000 to the year 2018. Regarding challenges and roadblocks, we have not received feedback regarding Sentinel Hub credits requested, as we are unaware if these credits will be assigned through an AWS account and what are the terms and conditions involved. Maybe they did send communication, but it did not reach me, Jimena Juarez. It is also worth repeating that for INEGI, it is not possible to receive the credits on an institutional account due to concerns raised by our legal department, so an internal agreement was reached for CONAVIO to receive and manage the credits. Regarding next steps and expected impact for our project, in 2021, we will continue to expand the data platform to host a set of products like land cover change and land cover. We are currently in talks with other federal agencies to provide visualization of other datasets like the National Forest and groundwater inventories, which will be presented in a special format. We will continue training models for audio and video processing, and we will engage with our Colombian colleagues and process the data provided by them. Then we expect to have an efficient processing pipeline running by mid-2021, which will allow rapid processing of our and also third-party audio and camera trap video data. Finally, we want to share our experiences with other countries from the region who may have similar needs.